Welcome to Yaka Digital Network. If you are spearfishing in a clear stream in western Uganda and aim your spear directly at the fish you see, you will miss. The fish appears higher than it actually is. That visual location is an optical illusion. This chart shows exactly why that happens. As light travels from the submerged fish through the denser water and hits the boundary of the less dense air, it speeds up and bends its trajectory. This bending of light as it changes optical mediums is called refraction. Looking closer at this boundary, we can draw a dashed perpendicular line called the normal. When the light ray exits the water, it bends away from this normal line. Because our brains assume light travels in a straight line, we trace that bent ray backward, making the fish look much closer to the surface than it really is. Our eyes are simply reacting to a change in light speed. By observing this physical shift, we can determine the math needed to correct for the illusion and predict exactly where the fish is located. Inside a Ugandan school laboratory, we can measure this bending precisely. Every transparent material has a specific mathematical signature called a refractive index. This value tells us exactly how much a material will slow down and bend the light passing through it. This diagram shows Snell's law in action through a rectangular glass block. We use the formula n equals sine I over sine r. In this equation, n is the refractive index, I is the angle of incidence where light enters, and r is the angle of refraction where it bends inside the block. When calculating these angles, there is a strict rule. You must always measure both the angle of incidence and the angle of refraction from the dashed normal line. You measure from the vertical line, never from the flat edge of the glass surface. Let's put this into practice. Grab a calculator and pause the video. If the angle of incidence is 45 degrees and the angle of refraction is 28 degrees, what is the refractive index of this glass block? Let's work it out together. You divide the sine of 45 by the sine of 28. That gives you 0.707 divided by 0.469. The result is exactly 1.5. Optical density behaves according to consistent rules. Every transparent medium on Earth has its own measurable refractive index that dictates how light behaves within it. Until now, we have tracked single rays of light, but sunlight, or pure white light, is actually a mixture of 7 different colors. When those colors hit a medium like rain after a Kampala downpour, they separate to form a rainbow. This animation shows a cross-section of a single raindrop acting as a tiny prism. When white light enters the water, it refracts. Because each color's wavelength travels at a slightly different speed inside the water, the light splits apart. It reflects off the back of the drop and refracts again as it exits, spraying into a wide spectrum. This splitting process is called dispersion. Notice how the spectrum always stays in the exact same order: red, orange, yellow, green, blue, indigo, and violet. Red light has the longest wavelength, so it is bent the least. Violet light has the shortest wavelength, forcing it to bend the most. This side-by-side comparison shows the difference between adding light and mixing paint. On the left, we see additive color mixing. Red, green, and blue are the true primary colors of light. When you overlap them, they create pure white light. On the right, subtractive mixing in an art class behaves completely differently. Mixing physical red, yellow, and blue paints absorbs light, resulting in a dark, muddy brown. Physical pigments subtract and absorb light to create darkness. Adding pure colored light together allows you to rebuild the complete visible spectrum. There is a specific condition where light cannot escape a medium at all. If light travels from a dense medium to a less dense one at a very shallow angle, it does not cross the boundary. Instead, it reflects entirely back inside, like a mirror. We call this total internal reflection. We can see total internal reflection happening in this cross-section of a fiber optic cable. The data is carried by a light pulse that reflects off the internal walls. Because the light is trapped, high-speed internet data can travel across Uganda over massive distances without the signal leaking out or degrading. Looking at our summary grid, we have covered 3 main principles. First, refraction is the bending of light measured from the normal line using Snell's law. Second, dispersion separates white light into a spectrum based on varying wavelengths. And third, additive mixing uses red, green, and blue light to build pure white light. Predicting how light behaves as it changes speed turns an optical illusion into a practical tool. These principles of bending and splitting light explain why we see rainbows after a storm, and how we maintain high-speed internet connections through glass fibers. Thank you for watching with the Yaka Digital Network. To watch more videos for all classes and access our complete library of content, visit us at www.yaka.cc.